everybody. So I recognize that there's a lot of information that we have to digest before we start talking about how to build an orbital rocket. And I figured the best way to do this is really go down to the fundamentals so we have a really good understanding about how to talk about things in the same language, communicate, and really just understand what we're doing. So the first thing I really want to get into is like the first principle, getting into space to begin with. You've all seen a parabola before. Now, the easiest way to reach space is 100 kilometers vertical. Just launch something that goes up and comes back down again. Of course, I'm greatly exaggerating this. You don't really want any horizontal motion. But let's say this is a distance time curve. So we launch the rocket. It exceeds 100 kilometers, which is commonly defined as the edge of space. It's called the Kármán line. And then it comes back down. How do we know how fast to get the rocket going so it gets up to that point? Well, you can model this very simply in the same fashion as a roller coaster. If you remember this from physics, there are two forms of energy we can talk about here. Kinetic energy and potential energy. I know this is sometimes rendered as U, but I think this is a little more clear. So kinetic energy is 1/2 mass velocity squared. We're not playing with relativistic speed, so this is fine. Potential energy is mass times gravity times height. And these two equations balance together in what's effectively a closed system. When we're dealing with lobbing this projectile into space, we'll treat the rocket as a projectile for all intents and purposes. We play with the balance of these two equations. We take one and we convert it into the other, and the other one converts it to the first again. So at the start, when the rocket is launched, let's assume it's already flying, it has a maximum kinetic energy and a minimum potential energy. When it reaches the top of its trajectory, it has a minimum kinetic energy and it has a maximum potential energy. So we set these equations equal to one another. Again, we're treating this as a closed system. We start with a closed system for kinetic energy, potential energy. We assume no losses. Not necessarily entirely realistic, as we'll get into, but for the sake of our first round analysis, this will be perfectly sufficient. So we take these two equations and we set them equal to one another. 1/2 mass velocity squared is equal to mass gravity height. And the first thing we can realize is that mass is on both sides of this equation. We can safely ignore it. In other words, the velocity we have to get up to is completely independent of the amount of mass that we're playing. It doesn't matter if we're playing with 10 kilograms or 100 kilograms or 1,000 kilograms. These equations and these numbers will come out the same. So we can safely substitute out mass, and then we treat the whole thing as simply 1/2 velocity squared is equal to gravity times height. And of course, we now recognize that the only variables that matter for getting ourselves into space are gravity and height, solving for velocity squared. So we can rearrange this. We can, of course, rewrite this as 2 times gravity times height, and the square root of that is equal to velocity. So now we can solve this. We know that the gravity of the surface of the Earth is 9.81 meters per second. We know we have to be consistent in our units, so we're going to be playing with 100,000 meters. And we take the square root of that function. Now, I don't have a calculator immediately on me, so I'm going to have to pull one out. But you can, of course, calculate this. What's the square root of 9.81 times 100,000? 1,000. And simply take this and get a better calculator. I should have bought an actual calculator for this lecture series, but we're going to play with this. So, there's a lot of people out there.
It's 990.
990. So, apologies for the loud people in the background, as some people aren't considerate to learning.
Okay.
Anyway, 990 meters per second. Thank you, Neymar. So, yeah, some people aren't considerate learning, but we'll keep going. 990 meters per second is our target velocity. If we cross through 990 meters per second, we will scrape the edge of the Kármán line and come back down to the surface of the Earth. Nice and simple. It's a nice, friendly number. But what do we do with this? What are our actual considerations when we start playing with this velocity? And we can think about this in completely different terms. It's not just velocity. We're starting from rest. Our rocket is not moving. Our rocket has no kinetic energy. So this is truly a change in velocity. And you may have heard of this term before. In a very, very famous equation, let me just clean off the blackboard before I introduce it. in the early 20th century, a very famous Russian mathematician named Konstantin Tsiolkovsky was one of the first people to really concretely derive the rocket equation and specifically use it as in the context of actual rocketry. And it looks something like this. A very simple, elegant, and beautiful equation that comes into being via calculus, but I'm not very good at calculus, so we won't step into that. Change in velocity is equal to the effective exhaust velocity of the rocket times the natural log of the starting total mass over the final total mass. Simple, elegant, beautiful. And what does it actually mean? Well, we can do to ourselves a rocket here. Newton's laws indicate that when we take mass and we throw it out the back, we get an equal and opposite reaction. We're losing mass. So we have a starting total mass, which is the rocket plus its propellant. That is m sub 0. And then m sub 1, which is just the rocket by itself without propellant. And this accelerates at some known velocity, which is what the effective exhaust velocity is. Very complicated term. We'll talk more about that in specifics in a moment. And of course, because calculus is involved, we're basically integrating this thing as a series of small changes. We can throw the complicated math away and treat it as a logarithm of the ratio between the two. And you may also have seen this expressed in a different way. And I think what is fundamentally for our purposes in designing an orbital rocket a much more intuitive and useful way of approaching it, which is you raise both sides of the power of E divided by the effective exhaust velocity, you get this. E to the power of delta V over V sub E is equal to m sub 0 over m sub 1. Why is this a little more powerful? Because it splits everything down to a fundamental ratio. In other words, this is what's called we can treat that ratio as R. And it makes everything very nice and handy because we're taking this term and we're reducing it down to a ratio between the starting total mass and the final total mass. And this ratio, for a given change in velocity and given engine performance, which is what effective exhaust velocity refers to, this will be true for any size of rocket. One that weighs 100 pounds, one that weighs 10,000 pounds, one that has a mass of 1,000,000 pounds. This ratio will be fundamentally true no matter what. But of course, we have to launch into effective exhaust velocity, which is that one mystery term that doesn't really have any real intuitive understanding of. Effective exhaust velocity comes into being because of the way that rockets are kind of categorized. There's this concept called specific impulse, and I'll clean off the blackboard as we walk into that. Specific impulse is basically an Earth-centric means of dealing with the performance of rockets. You may have seen this before, but it looks as IST. So it's the reason why it's called specific impulse. It has a unit of seconds because of unit cancellation. Because unit cancellation is painful and terrible, and I don't like to think about it very much. We can simply accept this as the word of God. So specific impulse was originally derived as a means of measuring the thrust per unit time of a rocket, more or less. In other words, when you talk about specific impulse, you're basically talking about how long you can sustain a certain amount of thrust before it burns out, and that's how rockets were originally categorized. Now, because this involves the weight of propellant, and weight is a function of gravity on Earth, this is very much a Earth-centric viewpoint. So what we do is we multiply the specific impulse by something that cancels out gravity, dividing by gravitational acceleration at 9.81, and then we get the effective exhaust velocity, which is a non-geocentric viewpoint on how an engine performs. Now, this is basically used as a performance number when it comes to rockets and rocket engines in general, because it's a very nice and friendly and simple unit. Generally speaking, when we talk about specific impulse, you'll see numbers thrown around from the 200 to the perhaps 460 range, and this is 460 seconds. Now, there are fundamental limitations with chemical rocket engines because chemistry can only get you so far, and you can only get a certain high level of an exhaust velocity because of chemical limitations, and you're just playing with the real world at that point. There are some theoretical compounds that can get specific impulses of into the 500-second range. They are single-handedly perhaps the most nasty combinations of chemicals that you can conceive of. There was one that I believe was, I think it used powdered aluminum to densify the propellant a little bit. It used fluorine and some other really unpleasant fuel, and it achieved a specific impulse of 520 seconds, but when they were testing the combination, it destroyed the test stand. Very nasty, very toxic. Don't play with those kind of chemicals. But when we're talking about our needs for orbital rocketry, we're mostly talking about solid propellants. And I think I should take a detour out of the fundamentals of orbital mechanics to really talk about what the difference in propellant is. So there's really three ways you can do this when it comes to designing a rocket. And each one of them have their pros and cons. And a lot of it relies on the concept of specific impulse and the concept of effective exhaust velocity. And counterintuitively, the fact that the lighter the molecules you're exhausting out of the back of your rocket, the faster you can accelerate them to, the higher your specific impulse. But that comes at a cost, which is reduced thrust. So, broadly speaking, there are three different classifications of rocket motors. Really real gas there. So there are solid motors. Solid motors are basically, they have a specific impulse of around 200 to perhaps 320 seconds. They're generally very powerful engines. You can get a lot of power out of a solid motor because it has very heavy exhaust products, and that's where you get your thrust from. Liquid motors are a little more free for. They have a little more range to them. They have a specific impulse that varies between as low as 200 seconds all the way up to about 460 seconds. And these numbers come in from the most high-performance rocket engines that we currently have available, which burn liquid oxygen and liquid hydrogen. And I mentioned in the comment a little bit offhand that I said about the lighter the exhaust molecules you're producing are, the higher your effective exhaust velocity is. That's why liquid hydrogen motors have the highest specific impulse out of any commonly used liquid rocket engine that we have in the world today. It's because their exhaust products are water and hydrogen gas, because they're not burned stoichiometrically. If you remember from chemistry, so if you do it stoichiometrically, you get, I believe it's just water and nothing else, because you're combining it in just the right ratio on the leftover products. But because when you're burning stoichiometrically, you get the highest possible temperature for that given chemical combination, you wind up in a position where your motor basically liquefies itself, and that's not really a good situation. So most rockets either operate fuel-rich or oxidizer-rich. And I will cover this more in a separate lecture series in the near future, but just to keep that principle in mind is like where we fall in the performance level. And there's hybrid motors. Hybrid motors are quite interesting. Solid motors have the fuel and oxidizer. We need both parts, as I didn't mention earlier, but should be evident, embedded in a matrix. And then you have an igniter that sparks it up and then allows the propellant to start burning. It's a self-sustaining process. You can't shut it off. And that's both good and bad. It means you can make solid motors very, very reliable, but you cannot control how much thrust they produce. Well, there's a consideration of that. We'll talk more about that in the future. You can't really control how much thrust they produce, and you can't shut them off. Of course, there are exceptions to this rule, and there are very technical engineering exceptions, but as a rule of thumb, you can't turn solid motors off. Liquid motors, on the other hand, are very nice. You can throttle them, you can turn them on and off, which means you can fire them multiple times. The propellants are generally easier to handle. You need an ignition system that's a little more complicated, but generally speaking, it's all very nice and relatively benign, except that the engines themselves are incredible masterworks of engineering, because you need to make sure you're delivering your fuel and your oxidizer in just the right proportions, just the right amounts, in just the right way, that they're all together in the right place. So when you spark up the igniter, they combust, they get a self-sustaining burn going, and you make sure that the combustion is actually stable. It's a lot harder to do in a liquid motor. So they have a lot of advantages, but a lot of disadvantages. And that's why most rockets in the world today use liquid motors, is because people are willing to put the development effort in because the benefits are so strong. And there's hybrid motors. Hybrid motors are kind of interesting because they're not really well classified in the world today. There are very few representations of hybrid rocket motors in general. Very few have flown on actual space flights. The only motor to actually do this is the one that's mounted to Virgin Galactic's Spaceship 2, which is previously scaled composite Spaceship 1's tech engine. Those are the only hybrid motors to reach space, and they have a specific impulse of, I believe, about 320 seconds-ish. They're not well quantified. And the reason why they're interesting is because they are more or less a hybrid between a solid and a liquid. You have a general case, this is not always true. I've not found anything in the literature that defies this, but I know that theoretically speaking, yes, this is possible, is that you have a liquid oxidizer of a solid fuel. And the reason why this is done is because you get the advantage of very high performance, you don't really have to dabble in very cold propellants, and so on and so forth. And I should probably take a quick detour to talk about cryogenic propellants. So, for the most part, liquid propellants need to be liquid because they're gases that are liquefied. That sounds really bad, and that's a really bad way of putting it, but those are very cold. You don't really have room temperature liquid fuels, with some niche exceptions. And I can talk a little bit about the propellant combinations, and I will do so in a future lecture, but generally speaking, the first one that comes to mind are things like alcohol and hydrogen peroxide, or unsymmetrical dihydrazine and aerosine 50, or they're a little more exotic. And some of those, a subset of liquid propellants are hypergolic propellants, which are incredibly nasty chemicals that you don't really want to be around. They can be stored long term, but in some cases they're so volatile and so potent that they will actually eat through the propellant tanks on rockets, which means they have to be changed out very frequently. A very famous example of this is the Delta II, which was just recently retired. They had an upper stage that burned hypergolic propellants. I think it was specifically unsymmetrical dihydrazine or aerosine 50. I always get those mixed up, and nitric acid. They had to change the stage out if it sat on the pad of fuel for more than 20 days, because it would dissolve and corrode the internals of that stage so badly that they would actually have to change it. So just a little footnote in the grand scheme of what these considerations are made for. There's a reason why we're playing specifically with solids when we talk about our orbital rocket project, and that entirely comes down to the fact that solids are relatively, not necessarily benign, but they're much easier to work with for amateurs. And almost all amateur rocketry dwells in the domain of solid propellants. So when we talk about getting to orbit and we talk about actually trying to deal with this is the domain that we really need to play with, because it's a lot easier to deal with. There is a very big fat asterisk to that, and I will talk about that in a future lecture. But for the most part, we are primarily playing with solids. All right, so apologies for the jump cut. We had some technical issues, but the thing I want to get into right now is some of the more hard math, or the more tricky to think about math, which is that space isn't really up; it's more sideways. In the very beginning of this lecture, I talked about that parabola example, the idea of going up and then back down again and skimming the edge of space. But obviously, not everything that goes to space does that, and obviously, the Earth is probably not flat, but this is definitely a little bit of a leap between going up and coming back down again versus actually staying in orbit. And staying in orbit, you have to think about it like Newton's cannonball. This is the Earth. We launch a rocket, it comes down, gets a little bit faster, finally fast enough that we actually stay in orbit. And fortunately, these are defined for us in very simple equations that have complicated derivations behind them, so I won't do them because they come from physics. Basically, if you've taken physics or physics 2, you will see them. So I won't worry too much about the derivations, also because I can't personally remember them off the top of my head, and I won't try to stress you guys out as I look at the board for confusion. But the next fundamental to talk about is, well, orbit itself. We are on a parabolic trajectory. We go up. We have to go sideways very fast. But how fast is fast? Fortunately, there is a very nice and simple way that we can quantify this. That is the velocity for a circular orbit. Simple, elegant, and pretty, but there's a mu in there. And that mu is a little scary if you ask me. What does it actually mean? Mu in this case, and I always write it backwards, I'm sorry for that, is equal to 3.986004441, sometimes 8 if you want to get really accurate and precision, times 10 to the 14. That's a big number, and that's not my phone number, so don't call it. But this is what's called the standard gravitational parameter, and if you recognize physics, you remember G times M. When we talk about very large objects or Newtonian gravity or anything like that, and this is basically the gravitational constant times the mass of the planet. This is a very specific number for Earth, and because we're dealing I think it's important that we focus almost entirely on using this number as as like, what we're playing with here. So I'm actually going to rearrange things on the board a little bit so we can have this number as a constant reference, and then I'll talk a little bit about actually using this in conjunction with what we're talking about. So I have it written down. I just don't want to keep looking at it in my notes. So 3.896004 418.
Was it 3.89 or 3.98?
3.98, thank you. So, and I'm going to also put the equation that we had as well. So V square root mu over R. And what exactly does R refer to? It's not the altitude of the orbit. It's the radius of the orbit. And the thing we have to keep in mind is that the Earth has some radius. In fact, specifically about 6.3 million meters. We factor in the radius of the Earth plus the altitude of our satellite. So which I'll simply write, and this will get confusing in a few moments, as R for radius and A for altitude. So we have to actually bear that in mind. And this concept will become important in a few moments when I talk about some special cases, because we're basically looking at the most simple and straightforward case of an orbit of some kind. And so we can very simply, plain and simple, do it. We know the radius of the Earth is equal to, as I have written here, 6.371 times 10 to the 6 meters. And let's say we want to get into orbit at 100 kilometers, which is actually the perfect number for this, because we're talking about our altitude is 100,000 meters. So, thus, we have our first two figures. We have our radius here and the altitude, which means we have to figure out what our total radius would be. So, we can just chuck this into scientific notation, or I'll just do this longhand because I like doing things longhand because I'm annoying. 1 million, and then we have 1 plus our orbital altitude. And now our orbital radius becomes 0, 0, 0, 1, 0, sorry, 7, 4, 6. And that is the R that's necessary for our equation. We want to talk about meters because this number is actually given in meters and seconds. It's a little bit weird because it's unit cancellation. I don't like to talk about unit cancellation that much, but just accept that is the fact, that is the truth, because that's the way that things work. It's very annoying though. So this is our radius, and I'll keep it in meters. I won't try and translate this into meters because it's a very annoying number to play with, but I encourage anyone in the audience to come up with our orbital velocity for that number, square root of mu over our target radius, which is 6, 4, 7, 1, 1, 2, 3. So, what is our target velocity then?
I got 7,848. Does that make sense?
Yes, it does.
Oh, yikes. That's fast.
Oh yes, that is very fast. That is about 20 fast. So, that is how fast we have to be going. That any object that is orbiting the Earth in a perfectly circular orbit, I stress perfectly circular orbit, will be traveling at 7,848 meters per second. Can you wiggle the mouse real fast? Just every like couple seconds or so. Very good, yeah. So that's really fast. That's blindly fast. And I don't really have a good analogy for how fast that is. Your car on the highway may be going only about 20 or 30 meters per second. So you're traveling really freaking fast when you're going around the Earth. So fast that you see 5 sunrises and sunsets per day. But this is only half of the problem. This is the velocity at 100, about 100 kilometers. And you remember from before that we had to put energy into the system to get up to 100 kilometers to begin with. We have to deal with it that way because the atmosphere is in the way. We can't just accelerate sideways and spiral our way out into space. We could, that'd be great, but there's real world considerations there. So we have to factor in that the minimum possible delta V, or at least a good approximation of the minimum possible delta V, is this value, our horizontal velocity value, plus the velocity we talked about at the beginning of the lecture, which is 990 meters per second. So factoring that in, 8, 4, 8 plus 990. 8, 4 plus 9 is 13. 8 plus 9 is 10 is 18.
And that 990 comes from the original calculation.
Yes, from original calculation of the altitude.
Okay.
So the delta V to reach orbit, the change of velocity from relative rest, is 8,838 meters per second. Compare that to the velocity delta V from just getting up in space to begin with. Space is really, really fast sideways. Very important to have that consideration in mind when we talk about these numbers. But of course, it's important to realize too, there's another aspect we have to discuss, which is, and we will discuss about orbital mechanics, not just launch, that most orbits aren't perfectly circular. This is basically a really ideal case. I will talk a little bit more about some of the considerations we make into deriving this and why the total delta V of some rockets may be higher or lower than this number. But we have to talk about our first real kind of weird case, which is an elliptical orbit. Elliptical orbits are malformed circular orbits. Now, if you remember from physics, all orbits can be defined as a function of a conic section. You take an imaginary cone and you slice it through the plane at different angles, you'll get an ellipse that can be rendered as an orbit. And whenever we talk about orbits, we have to think about them as ellipses with the body of interest at one focus and another focus that doesn't really do anything. It's purely a mathematical value just kind of there. And there's a little object going around and a happy little circling around in a happy little prograde orbit. So elliptical orbits are kind of interesting because of that. Now, what that means is that the velocity for an elliptical orbit actually changes, and a very famous individual named Johannes Kepler, who I'm sure you've probably heard of, is one of the first people to talk about this in any real sense. Oh, should I erase that? I probably shouldn't have erased that, but that's okay. And one, of course, Kepler's law, as you recall, the one that goes that an object that orbits another body must sweep out a line that, like basically a polygon of equal area at all times throughout the orbit. And what that means is that you go very fast when you're close to the planetary body and very slow when you're very far away from it. But there's a hidden reason as to why this is the case. It's basically the same things we talked about at the very beginning of this lecture, the idea of the exchange between kinetic energy and potential energy. You have to have some kind of kinetic energy to stay in orbit, and you're exchanging that for potential energy to get farther away from the body. And because an object in orbit is a closed system, you're not adding or subtracting any energy as it's circling around the Earth. What that means is that an object that's very far away will go very slow, and an object very close will go very fast, and you can predict that very reliably. And we actually have special names to the maximum and minimum altitudes that we deal with. We have an apogee and a perigee. Which I don't know if you've probably heard of before, but if you play Kerbal Space Program, you've heard of apoapsis and periapsis. Apoapsis and periapsis are the non-Latinized possessive versions of apogee and perigee. You can use apoapsis and periapsis very generically. But apogee and perigee, well, it refers to the Earth. It's got the G in the word. So when we talk about orbits, we generally see them as referred to as perhaps something like 1720 by 290 or some number like that. If you've ever talked about orbits or seen them referenced in literature, you'll see, and that's kilometers. And that is literally the apogee by the perigee. That's how we reference orbits. These two are always exactly 180 degrees away from one another. There are no exceptions to that rule ever, period, and full stop. And they all kind of, they'll all align in the same way. But of course, there's another aspect we have to talk about, which is, well, as I said before, the velocity problem. You can't really talk about velocity because there's no concrete velocity. When I mentioned the circular orbits before, the reason why we can solve so nicely for velocity is because it's constant across the entire orbit. We don't really care where it is. Wherever it is in that orbit, it'll be the same. But as we just talked about before with Kepler's laws and the exchange of potential and kinetic energy, it'll be going faster here and slower here. That's a lot harder to deal with. So the way that we actually really get invested in this is we look at our satellite, which is, say, right here, and we have the radius between the center of the planet in question, which is generally at one of the focuses of the ellipse. We have a mu value. We take the ellipse and we split it into geometric halves. I'll use A again because it's the best way I can represent it. That called the semi-major axis. The semi-major axis of an ellipse is basically the long axis of it cut in half. It's like the radius of the long axis. This is rather important because, as you'll see, the circular form of it, the radius is the semi-major axis. We don't really care about what else is going on. But the velocity is dependent as a function of its position in orbit. So the way that we actually look at this is what's called the vis-viva equation, which is a very old term. It comes from Latin. It means energy of life, basically. You've heard of viva, vita. It's all kind of in the same linguistic family there. So we actually use this equation to talk about the instantaneous velocity based off of the position of the object, which Vr is equal to the square root of mu, remember mu, times, as I have written here, 2 over r is 1 over a. And that will determine your velocity instantaneously at any distance from that main point. And of course, you can kind of see where the v is equal to the square root of mu over r kind of comes in, because at the point in which you're dealing with a circle, r is equal to a. So it kind of becomes 2 over a minus 1 over a, and that just becomes 1 over a, and then, well, I can just do it right here. So in a situation where r equals a, Vr is equal to the square root of mu times 2 over a minus 1 over a. 2 minus 1 is 1, so that just becomes the square root of mu over a, which is the radius at that point.
Which is the original equation.
Indeed it is. So you can see how we can go from the complicated case and come back to our first simple case just by a little bit of substitution. I think that's one of the most beautiful little proofs that I can talk about today. So that defines our properties. And what we can actually do then is, because we now know this equation, we can calculate our velocity at periapsis and apoapsis and any other point along the orbit as long as we know the distance from the target body. And what that means is that we can actually do things like maneuvers. We can calculate, if we're at perigee, how much energy, how much of a change in velocity do we have to put into the system to kick our apogee up to a certain point, or down to a certain point, or vice versa. We can now do that with the vis-viva equation, which is one of the most powerful tools that you'll come in contact with when we talk about orbital mechanics. And that leads me to my next little subset of orbital mechanics as a discussion, which is the idea of reference frames. That was a bit of a jump cut. All right, so the big thing to talk about now is how do we actually know where we are in space? What terms do we use to define our position in space and our orientation relative to an orbit? So, show of hands real fast, how many of you played Kerbal Space Program before? All right, that's fine, but we'll talk about it, and if you've played a KSP before, you'll know exactly what I'm talking about. So this is our very exaggerated orbit around planet. So I'll just call it E for Earth, because why not? Generally speaking, most of the time, because we follow the rotation of the Earth, we are going in this direction, so I will assign this as our orbital direction. As time goes on, we will circle around the Earth. Sunrise to sunset. Yada yada, so on and so forth. This is called prograde, and I'll write it out for you.
What did I miss?
Prograde. So prograde is basically the direction in which we are heading at this current time. It is the direction of the orbit, direction we pass through. If you were riding along, you would be going prograde. It's like if you're on a highway, the direction of the flow of traffic, that's prograde. This also has a colliery, which is called retrograde. Which is backwards. These are the first two directions that we talk about when we talk about prograde and retrograde. And if you can imagine, if you have a rocket, you're pointing along prograde and you fire the engine, you will accelerate, you will speed up. The other side of your orbit will change in response to the vis-viva equation that we talked about earlier. If you're pointing in retrograde and you fire your engine in the opposite direction, you will slow down. The other side of your orbit will decrease in altitude in accordance to the vis-viva equation. Same principles, just now we have terms to talk about them. There are also 4 other directions to discuss. We have radial in and radial out, which is basically pointing directly at the planet in question or directly away from the planet in question. You may also hear the term zenith and nadir referred to as well, like with this being zenith and this being nadir. I don't know how to pronounce it. Nadir. It's something. Does anyone know how to pronounce that? Nadir. that's okay. So, and that's in reference, like you imagine tilting yourself around. So you were sitting on your orbit, zenith is above your head, nadir is to your feet. And you'll hear this a lot when we talk about the International Space Station and like zenith ports, nadir ports, so on and so forth. Same principle there. There's one final direction to speak of, which is coming directly in and out of the blackboard, which is normal and anti-normal. And those are basically, if you have the reference plane here, normal is coming out at you, anti-normal is coming towards you. You might ask, what happens if you point your rocket in those directions? And I'll specifically talk about normal and anti-normal because it'll launch directly into our next topic from there, pun intended. So if you have a rocket and you point your rocket upward along the orbit, or it is this way, you basically change the inclination of your orbit. You add a new vector that comes in, and the sum of those two vectors means that you're now in an inclined orbit. Congratulations. Nice, simple, and straightforward. The specific values that you get for two circular orbits, I won't get into the elliptical case because that gets real hairy real fast, but the simple direct case is that you can approximate the change in velocity needed for this as 2v, which is your current velocity in your orbit. That's the one we talked about earlier, the functions of a circular orbit. I'll make a gesture, but that's okay. 2v sine the ratio of our change in inclination over 2. This is the most delta V intensive maneuver you can ever do second to landing on a planetary body. You don't want to do that. I mean, you can imagine, like, if your inclination change is really severe, like in tens or hundreds, pretty severe, it gets really big real fast, and it's a function of your velocity in your orbit. So it's in addition to that you're dealing with this. So it's a very, very large number. And generally speaking, we always try to avoid doing plane changes, which actually launches directly into the topic of, launch. And I'll walk you through the orbital mechanics consideration. We go from ignition all the way through to burnout, and that'll be a fun little way to, I think, conclude this specific lecture. So, let's start with launch. I'll talk about the engineering considerations that go into these things in the next lecture, but specifically this one, we can talk about it starting off from a somewhat flat surface. We launch our rocket. It goes up. It goes against gravity. We want it to go up because the atmosphere has some kind of thickness. The thickness of the atmosphere looks something like this. We want to reduce two forms of drag. There's aerodynamic drag, which we're all familiar with. We all know and love. It's 1/2 CDA rho velocity squared. But there's also gravity drag. And you have to think about it like this. If you're hovering something in the Earth's gravitational field, and for the purpose of this, I'll consider Earth's gravity to be constant from the surface up to space, which pretty much is. It's off by maybe a couple tenths, or it's a little bit lower because you're going farther away from the center of mass of the planet, but we can almost ignore it. So you're hovering on the Earth, in the Earth's gravity field. That means you're actually accelerating upwards at 9.81 meters per second to cancel out the acceleration downwards at 9.81 meters per second. And what that means is that you're actually putting some kind of change in velocity into your system to keep yourself floating. But that's not necessarily, that's something you have to consider across the entire burn time of your rocket. If your velocity points straight up, the more you have to deal with it. You think about it, 9.81 meters per second squared. Every second you're burning the engines. You are accelerating upward. You're fighting that acceleration. So you can assume approximately a 10-second period, you've lost 98 meters per second of your velocity to gravity drag. So you can't point yourself vertical the whole time. You want to be horizontal. It's the most efficient way that you can burn your stage and keep everything happy-go-lucky going in a circle. But you can't do it because the atmosphere is in the way. So you have to go up for some point. You have to basically fine-tune the balance between when you're going vertical and when you're going horizontal. And that, of course, leads me into the next concept, which is that of the gravity term. This is a bit of a fun one because I didn't fully understand this until I actually sat down and looked into it. But you notice that most rockets will start pitching over after launch. They'll launch vertical and they'll start pitching. And that's not actually an aerodynamic process at all. It looks like it's an aerodynamic process. You'd imagine it would be, but it's not. Because, and this I'm a little excited about this. So when you're going upward, your gravity losses are pointing this way. Your velocity vector is this way. You're pointing this way. The rocket is, of course, pointing vertical. That's really, pointing vertically. But when you turn over a little bit, only by a couple degrees, suddenly you have this vector, that vector added on to the end, the resultant velocity is angled as you pitch the rocket over. Because now your gravity, the vector from gravity is now doing this. You're doing the sum of those two. And this happens again and again. And so basically the effect is that you turn your trajectory as you go upwards. Which is probably one of my favorite little, not directly intuitive, but makes total sense when you think about it kind of deals. And this is something that is true. You can do this on an airless body. If you're on the moon or something like that, you can do a gravity turn just fine. And again, for those of you who play Kerbal Space Program, you know you can do this on airless bodies. And yes.
So basically, if you start pitching even a little bit, it's gonna
it'll be
force you to go horizontal.
Yeah, it'll be a self-feeding cycle unless you have some sort of active control system. And there's a reason why you do a gravity turn specifically. Oh yes, I'm sorry, there's another question. Yes.
What is forcing you to burn in the prograde direction, though?
In what sense?
Like when you're in the atmosphere on Earth, you are forced to burn in the prograde direction because in the atmosphere. But when you're on the moon, when you pitch over a little bit, there's nothing else forcing you to keep turning. You don't have to burn.
Gravity vector.
That's the force on the rocket. That's not the.
That's what actually tweaks your trajectory over is that little vector coming in and pulling it. It's really weird. Like it doesn't make sense when you first look at it, but it's completely true. Yeah, that whip was a little subtler. But anyway, so that is how we get a trajectory going in a beautiful, nice arc. And then, of course, we have to get into, well, you derailed my train of thought there. So that's one important consideration we deal with when we're talking about the actual gravity turn. So it's all fine. We're going up. We're turning this way. We're getting a beautiful little arc. You can integrate all the little things, and you have to do it numerically for some reason because that's just the way calculus works. And eventually you hit a point in which you're going mostly horizontal. Everything you're summing at that point is going horizontal. You're circularizing your orbit. And you might first think to yourself, well, first we were going from a parabola, and then we're going into an orbit. Well, that doesn't make any sense. It's not a conic section. It is a conic section. You're only seeing a very tiny expression of it, though, because the rest of it's inside the Earth, and you can't orbit through rock. At least I'm pretty sure you can. But I would be the person to ask about that. So eventually the rocket comes up, goes around, curves over, it's going largely horizontally, and by the time it burns out, you've put enough velocity into the system that it makes a nice circular orbit. And that's basically the gist of the launch process. Of course, there's some special considerations, like how do you control the thing on the way up? How do you actually do this pitch over? The pitch over program is usually something that's programmed into the vehicle from the start. Like you'll run dozens of simulations on these things, and you'll figure out, okay, this is how it's going to go. In fact, the first stage of the Saturn V had a completely pre-programmed trajectory. It didn't, as far as I'm aware, respond to any outside external influence, because there's really kind of two ways to do guidance, and this is dabbling in the engineering bit, but you basically can have closed loop and open loop. Closed loop is basically you assume everything works perfectly, spherical cow in a vacuum scenario, everything's nice, happy, and good, and functional. The flip side of that is that the real world is not. The real world does not work perfectly. The real world is flawed. It has all kinds of little things. You deal with things like wind shear. So then you start talking about active loop, and that means you look at the environment. You have an idea of where you're supposed to be. You register yourself in the environment with your position and velocity and these other things. That's going to be something for the engineering considerations lecture. And you play with the numbers for a little while, and you basically come up with a system that's self-correcting. It's not entirely perfect because nothing is entirely perfect, but that's where you start talking about PID loops and such.
So the blind system is called open loop?
The blind system is closed loop. Oh, okay. Okay, fine. Okay, fine. I got a correction from the audience, but the blind system is in fact open loop. Yeah. Thank you, Mr. Parfilko. Credit Anthony Parfilko for filling in on this one. So that's basically just aware of what the considerations are. You get the thing, you launch it up, you come to a certain point, you figure out where you need to do the pitch kick, you slowly kind of arc over, and then you burn out, hopefully in a position where you're in orbit. Now, consider a little asterisk to talk about here. The kind of rocket that we're talking about building is not necessarily something that has thrust vectoring capability available to it, because doing thrust vectoring on rockets, which is one way of controlling them, is really, really hard to do on solids because you have a very hot nozzle that has to be flexible. So there's a couple different approaches to this. So you can have fins fins are nice. They're simple. We know about fins. We know about all moving control surfaces. It's a very well documented example of something in the realm of aerodynamics. Problem is they stop working when the atmosphere stops working. So bit of a downside there. So that's where you start talking about using vanes. And the V2 rocket from the very end of World War II actually uses this, and some of the early American rockets use something like this, where you would have a rudder in the exhaust path of the engine, and you would use steer the rudder to deflect the exhaust in whatever direction you need to control it. And that works fine and good, but the problem is these are fragile. These break easily. So you could have a situation where, God forbid, one of these things burns off, then you lose control entirely, and that's game over for you, and you can't fall back on the fins because the fins don't work anymore because you're in really thin atmosphere. So, bit of a problem there. So most rockets generally do is they will do something, they will actually physically take the entire motor, and this is especially true for liquid rockets, and they will have actuators built into it, and they will push and pull the rocket motor itself around. They will vector the thrust in order to steer it. You can't do this with solids because solids are one homogeneous case, and well, actually it's very hard to do with solids. And you have to actually move the nozzle. A solid motor is the sum of the propellant casing and the nozzle itself, and the nozzle itself can be made flexible. That's a really tricky joint to deal with because you're talking very high temperature gases playing in an area that doesn't like to have very high temperature gases in it. So that becomes a very huge engineering challenge. So it becomes a little bit difficult to talk about the active control needed to make sure everything stays nice and happy. There's a few techniques that real-world rockets use, and I'll talk about these more in the engineering lecture, but it's just an important consideration because you do need some control capability in order to get it into position. For our purposes, though, we actually want to look at what Japan does. Japan, after the end of World War II, was forbidden from developing guidance systems in rockets because, World War II happened. So what they were forced to do when they were starting their space research programs in the middle of the 20th century is they decided to build a system that was almost completely passive. And it still consists to this day, for their very light sounding rockets, of a guidance rail that's angled over a few degrees. That serves as the pitch kick function, more or less. So it's already pre-programmed in when it's launched. It starts in that position, gravity pulls it over in a nice little arc, and it reaches orbit, which I think is pretty cool. And you can also do that to get around, and this is again something with the engineering considerations lecture, you use that to get around like local atmospheric stuff like wind gusts and things like that. You can angle yourself into the wind stream a little bit for very light rockets, but that is again something you can consider when I talk about when I go into the engineering considerations, because that'll be that's a little more involved and a little more like actual, instead of mathematical theory, it's a little more like actual engineering. What do people do? But so in a nutshell, those are the considerations that we make, and let's go over what we talked about today. Sweet, Jesus, I hope we can cut that. All right.
I'll leave that in.
Yeah, we can fix that in post. So, what did we really talk about today? We discussed the fundamentals of getting up to altitude. We discussed the fundamentals of getting into a circular orbit. We came up with a minimum value of the delta V needed to reach orbit. We talked a little about elliptical orbits and the assumptions that we make when we deal with them. We talked about vis viva, which is really important for maneuvers. And we discussed some of the fundamental principles of how to actually get a rocket into orbit and what it actually looks like from a very high-level, simple mathematical conceptual stage. But I would actually like to launch into a little bit of a bonus lecture here, which is the idea of orbital rendezvous. This isn't strictly necessary for our purposes, but I think this makes it a little great way to talk about a lot of things we've discussed. Orbital rendezvous, very fun topic, not something that was immediately intuitively understood at the start of the space age, and also was just a really, really new thing to talk about. So, let's say you're a spacecraft in space, and you want to go visit a space station that's in another orbit from yours. How do you get to it? Well, we have to look this. I'm going to exaggerate this a little bit. Yeah, you really can't tell those apart. All right, I'll just use dash lines. So let's say you are here, and you want to get to a space station that's hanging out, somewhere in that orbit. How do you get to it? Well, the first thing you have to realize is that orbits are not at all intuitive. We talked about this a little bit in the when I talked about the circular orbits equation. We're going to assume we're in a circular orbit. So again, I asked for audience participation in this fun part, which is where we assume V is equal to the square root of mu over r. assumed radius of the first target interceptor is, let's say, 100 kilometers altitude, and the target that we want to be at, which is triangle one, is at, let's say, 200. Wait, that's meters? So let's run through some of the little mathematics on this. So first things first, we know mu from our previous discussions on, which is 3 point, oh boy, here we go, it's a long string.
3.986
0
0
0
4418
times 10 to the 14. That's a 14. So we know mu, we know these values. So what then is our velocity, a circular orbit, like our, spatially independent velocity for R1 and R2?
300,000.
Pull out your calculators.
Oh, the velocity. I thought you meant the radius.
Yeah, so I'm solving for the velocity for this one and this one, and I'll just trust your judgments to actually do calculations. I didn't bring a calculator with me. Okay, so actually we talked a little bit about this during the quick break that we had, but the velocity for the first object is 7,848 meters per second, and the velocity for the second is 7,788 meters per second. And that seems weird because the one that's farther out is going slower, because this is the velocity of the space station. And what that means is that, number one, we will circle around the Earth more frequently than the space station does in the same amount of time. And number two, it means that we have to make a very important consideration, is that we can't really just burn straight at it. To catch up to it, we actually have to wait for us to go a little bit faster. If we wanted to approach the station in some way, shape, or form, we have to go to a lower orbit to speed up and a higher orbit to slow down. Completely counterintuitive. And this is one of the biggest things that tripped up people at the very start of the space age, because this wasn't immediately intuitive and understood. We didn't actually know how rendezvous and docking worked until we started getting into it, like for realsies, and that's why the Vakshad program, the Soviet Union, and the early Soyuz program, the Soviet Union, and the Gemini program, the United States, both existed, because it was ironing out the kinks and fundamentals of orbital rendezvous. The Soviets had a head start on understanding it, but and actually pulled off docking first. If you remember, no, I think we pulled off docking first, but it's a historical footnote. We'll get into the history in the third lecture. So that is the two basic big fundamental numbers. And what we have to do is we have to now reach this this target. And we have to time ourselves right so that we basically come right up to it as it's in the right place. Now, because both of these are moving or circling around, we basically have to do things such that we're right next to it by the time we basically pass right next to it, and then we can match orbits with it, and we'll be in the same orbit, and then everything else is kind of more or less as you'd expect intuitively. So how do we do that? There's a very, very famous example of this. Is an orbit that passes at both this position and that position. And that's called a Hohmann transfer. I think I'm spelling this wrong. Please spell check me if I've spelled that wrong. Am I good? Excellent. So that's called a Hohmann transfer. The very straightforward and direct way of doing it, it's a geometrically very consistent and reliable way of doing it, and most rendezvous and most orbital maneuvering is handled through a Hohmann transfer. There are some exceptions. There's always exceptions to every rule, but we'll get into those in the future. And for the sake of this argument, we'll just talk purely about a Hohmann transfer. So what a Hohmann transfer does is it connects two orbits, one lower and one higher. You have a target in the higher altitude and an interceptor at the lower altitude. So the question is basically at what point do we burn our engines so we can actually match the target? Because if the target's too far ahead, then the target will be too far ahead and in the wrong position when it's up here. We're basically slowing down to meet it. So we actually have to be ahead of it. No, it has to be ahead of us very slightly because we'll cover the same distance in a little bit less time. It's also a slightly shorter distance, so on and so forth. So how do we quantify this then? How do we know what position the target has to be in so that it'll cross this distance in the orbit at the same time we cross this distance in our orbit? Because again, we go back to the lecture from apoapsis and periapsis. We are functionally going to be at the periapsis of this orbit, and we want our apoapsis to match the orbit of the target vehicle. So we can look at this from a new equation I'm going to chuck at you, which is the time that it takes to an orbital period. So an orbital period is defined as the time is equal to 2 pi times the square root of a cubed over mu.
This is way more interesting than psych stats.
I'm glad. So time is equal to 2 pi times a cubed over mu. And we talked about a cubed before. We look at an elliptical orbit. A is the semi-major axis. And this is also the semi-major axis, or in the case of a circle where the radius is the semi-major axis and vice versa, we use the radius. But this will determine our time. Now, we are crossing through half of an orbit up to this point. We're not going through a full orbit. We're only going through half of it, and we are going through exactly half, so that way we go from our periapsis to our apoapsis, and the target vehicle will be at apoapsis.
Sorry to interrupt.
Yes.
Could you just point out which of the lines is A?
Oh, this one? Sorry, thank you.
Is that one?
This is A. Cool. Our semi-major axis, the half of the long side of the ellipse. So, we pick ourselves up to apoapsis. We need to know when to do it, and we can back calculate the position that this spacecraft needs to be in order to meet it. And we can also introduce the concept of the phase angle. The phase angle being what angular position difference do we have to be between us and the target in order to actually meet it. So we look at this equation. Our orbital period for our elliptical orbit is the semi-major axis. What is the semi-major axis? A little bit of a problem there because it's not just the radius. We have an elliptical orbit here. So we have to look at it such that it is the sum of the total difference, this radius plus this radius, divided by 2. That will yield the semi-major axis of the ellipse. And that will determine our orbital period. And then we divide that by 2, and that will yield our, that'll yield how much time that we have between this point and that point, and how far back this will be, the first step of our calculation. So, but we already know these values, and I'm going to rewrite them in their actual radial values, which I should have done in the first place. Very good catch on that. But we will actually look at the, do we need this?
Yes.
Yeah, we need this, thank you. All right, we'll keep that up there, but we'll rewrite this in our correct values. So the first R1, which is the radius of the target, is 6471 meters. And then R2 is 6571 meters. So simply, we add them up and divide them by 2. What is the average of these two values then?
The first one plus
6521.
6521? So the semi-major axis of our transfer orbit, and I'll rewrite this in a few seconds, p equals to 2 pi square root of a cubed over mu. So our axis, semi-major axis, is then, which that was?
6521.
6521, 0, 0, 0 meters. And that is that difference. So now what we can do is it's simple, we can convert this into half time. Times 1/2 of the order is t over 2, so just pi times the square root of a to the third over mu. So run this calculation with this axis and figure out how much time you get. I figure
This gives us the
this gives us the amount of time that we have, and then we can back calculate it into the orbit of the target.
how much time it'll take to go from the edge of
How much time it'll take
1.
from here to here. Yeah.
Okay.
the Google calculator.
Sorry, the half time is just pi times a cubed over mu, and mu I have up there still, so it'll register in seconds. Thanks, unit cancellation.
And, 5,240 or 441.
5,241 seconds. Does that seem like a reasonable number? Well, we know that it takes about 90 minutes for something to circle the Earth, give or take. 5241 divides that by 600.
That's like an hour and a half right there.
Shouldn't it be closer to 45 minutes? Did you do full time or did you do half time?
Oh, full time.
Okay, so just divide that by 2. All right, wonderful. Because I think that seems like an hour and a half, so that would be like what?
2,620.
So we have 2,620 seconds from this point until this point, which means that this object needs to be 2,620 seconds away from hitting that same point. So this is 180 degrees. We can do this as a degree thing. There should be a way to, remember, seriously, right, we can do this as actually do let's do the period of the target then. Because we got our orbit, we got this one. So just plug in this for A and give me the full time for that. It should be like about 5,000 something.
Yeah, 5,301.
So the time it takes for the target vehicle to complete one orbit is 5,301 seconds. So then what is our angular velocity? That would be distance, which is 360 degrees over time. So how many degrees per second do we cross through then?
That's not how you do it.
All right, how do I do it then?
You take the time it takes for you to do that transfer orbit.
Yeah.
You divide.
Right. Well, because we need to know the angular velocity if I'm coming up with it in angular degrees. Because we know it completes 360 degrees of an orbit in 5,000 seconds.
Yeah. Or
So in 1 second, how many degrees it covers?
How much time does it cross through 1 second? I probably wrote that backwards.
No, that's if you're looking for 1
Yeah,
second.
yeah,
Then
1
yeah, that's
second.
right.
Yeah, time for one.
Yeah, so that would be
Time per degree.
time per second.
So you
Yes,
get
1 second.
it's 0.068 degrees per second.
So now we have that. So that's our degrees per second. So then how many degrees does it cross through in the amount of time that we have available in that half orbit?
178 degrees. Oh, it's 7.9, but
Well, what did you say it was?
177.9.
Now let's use that. So that means that, in conclusion, our target vehicle has to be 177.9 degrees away from the point that we meet before we start our burn and enter the home and transfer.
How many degrees ahead of us is it?
Well, then that would just be 177.9 minus 180. Well, 180 minus that, I'm sorry. Math ain't my strong suit. Kind of ironic, isn't it? So that's like about
2.1.
2.1 degrees out of us.
So once
And
so
that
once
is our
that
answer.
vehicle is 2.1 degrees ahead of us,
This
that's
vehicle
when
is
you can
2.1 degrees ahead of us, then we make our burn and we'll meet it at Apoapsis with some error here or there.
Wow.
And it's a very simple approach because realistically speaking, we have to talk about plane changes and stuff, which is really, well, plane changes and inclination and stuff, but why are you scared about it? It's just plane changes. So I got some fear in the audience about that, but so I think that really just covers all of the topics I wanted to talk about today, plus the bonus lecture for this stuff. I wanted to get a little bit into the plane changes stuff to give an idea of like inclination, because we're looking at all this stuff two-dimensionally, but when we're talking about actually getting to orbit, it's three-dimensional. So maybe I'll save some of that for next lecture when we make some considerations. I can talk about things like rate ascension of ascending node and some more of the principles. But this will give you a fundamental approach of the mathematical language that we're talking about here and kind of what we're looking at from that high-level perspective. So thanks for coming out today. It was really great to have the audience that I did have. For those of you watching this recording, I hope you enjoy this, and have a great day. See you in the next lecture.